Hi everyone, PGS members and everyone. There's a quick announcement before we start the presentation today. This is on the VGS symposium. Just a reminder on the VGS symposium on risk and liability will be held on May 29th, and early bird registration for the symposium will be end on April 30th. So just a reminder on the early bird registration and also the symposium. I will send out a reminder email by end of this week. With that one, I'm glad to introduce our presenter today, Dr. Arash Khosraw-Vifar. Arash received his bachelor's and master's degrees in civil engineering from University of Technology, Iran, and PhD from University of California, Davis. Following his PhD in 2012, he joined Fugro Consulting in Oakland, California, and worked there until 2016 before he became faculty at Portland State University. Arash's PhD work research is on design of piles subject to liquefaction-induced lateral spreading, which was supervised by Professor Ross Boulanger at UC Davis. Following completion of his PhD work, Arash continued to working on different highway, bridge, and maritime transportation projects that involve various aspects of seismic pile behaviors in liquefied soils. Today, Arash will be presenting design of pile-supported wharfs subject to inertial loads and liquefaction-induced kinematic loads. With that, on behalf of Vancouver Geotechnical Society, we welcome Dr. Arash Khosraw-Vifar to deliver his presentation. Over to you, Arash.
All right. Well, hello, everyone from Portland, Oregon, and thank you for inviting me to share with you the results of a research study that we started about 4 years ago when our collaborators, Steve Dickinson, Scott Schlichter, and Nathan McCollum basically handed over a wealth of data on 5 centrifuge tests that they had performed in 1999 to 2001 on pile-supported wharfs. And that's started this collaborative work. I want to give a shout out to Milad Suri, who is the PhD student who did most of the work that I'll be presenting today, and in fact, he's defending his PhD tomorrow. So to start with, there are many case histories where which documented collapse of piles due to lateral spreading. You're all familiar with this example of the Showa Bridge that collapsed in the 1964 Niigata earthquake, where excessive deformations in piles due to lateral spreading, liquefaction-induced lateral spreading resulted in the collapse of the bridge. Here is another example from the Port of Oakland that suffered a lot of damage in 1989 Loma Prieta earthquake with those examples of shear failures at top of the piles. And there are many case histories that have documented this case. And there are cases that the piles were actually designed to sustain those loads too. So this is one example that was documented by Professor Finn from the 1983 earthquake in Japan, where the approaching embankment failed due to lateral spreading induced by liquefaction, but the piles themselves were didn't fail, and they were designed to take the loads based on the inertial load from the earthquake shaking and the lateral spreading loads from ground deformations separately. Which takes us to the question that we are trying to address in this study, that should inertial load and the lateral ground deformations be additive in design? Are they in phase or out of phase? You're all familiar with this example, this drawing from Brandenburg et al., where you have piles going through what we call a multi-layer liquefiable soil, a non-liquefiable crust sitting on liquefiable soil, and at the bottom a competent soil that does not liquefy. So when it's sitting in a gently sloped ground, that top non-liquefiable crust slides down and exerts a huge load on the piles. So the load from the lateral spreading is in this case downslope, and the inertial load from the mass and the acceleration on the deck mass is also in the downslope. So we want to see, we use these 5 centrifuge tests that I mentioned to see if that is the same response that we observe in those tests. Are these two loads in phase or are they going out of phase? The other thing that we want to discuss is how to design them. A lot of you know we've experienced that with this type of analysis, where sometimes you apply the lateral spreading demands as a displacement to the end node of PY springs. LPIL has made it very easy. You just apply it as a soil displacement. Sometimes you apply it as a limit earth pressure. So we want to see if that is applicable in our case, and you'll see in the test that we analyzed, this ended up being overly conservative, and I'll show you why in a few slides. So we also wanted to back calculate these load combination factors, 100% of kinematic plus some percentage of inertia. We want to see what those combination factors are in reference and combined to other combination factors that have been developed primarily based on the research projects that have been done on highway bridge foundations, namely the Caltrans 2012 study. And at the end, we also wanted to see if the long duration earthquakes from subduction zone earthquakes will have any effect on this combination of inertia and kinematic. In Oregon and Pacific Northwest, we are dealing with Cascadia subduction zone with earthquake duration, strong motion duration up to 2 to 4 minutes. So we wanted to see if there is an increased likelihood with the inertia and kinematic loads to interact when you're dealing with larger or longer duration earthquakes. So I've listed here some of the design codes that we were able to compile and in terms of specifically on the combination factors on inertia and kinematic. There are tons of research studies that have investigated it. I'm not listing them here. I'm only listing the design codes and standards to see what they say on liquefaction and on inertia and kinematic interactions. So AC61 2014, which is the code for ports and wharves, and Port of Long Beach wharf design criteria, the 2015 study, mention that the two loads, meaning inertia and kinematic, do not need to be superimposed. They say that the maximum moments occur at different times and the two loads should be treated uncoupled for marginal wharfs. Port of Anchorage seismic design manual recommends combining peak inertia with 100% of peak kinematic. They allow going to use smaller factors if you use 2D nonlinear dynamic analysis, but no less than 25%. AASHTO 2014 still treats the two loads as uncoupled, and it only says that the simultaneous effect of inertia and lateral spreading loads should be considered only for large magnitude earthquakes, for a reason that we all know, because of longer durations. MCER ATC 2003, this is one of the earlier studies that really addressed this issue. They suggested that the two loads should be the design files for independent effect of inertia and lateral spreading, but they did mention that for large magnitude and long duration earthquakes, the two loads may interact. This is the peer study 2011, or the Ashford et al. Report, which recommends 100% of kinematic load plus something between 65 to 85% of inertia multiplied by another factor due to the effect of liquefaction, so 35% to 1.4. Well, Caltrans took these two and simplified it into what you all know is the 100% kinematic plus 50% inertia. And that has been adopted by Oregon DOT. And recently I've been trying to see what the Canadian codes suggest, and the supplement to the Canadian Highway Bridge Design Code adopts the same load combinations too, or recommends the same load combination factors. On the other hand, Washington DOT uses a lower combination factors, 100% kinematic and 25% of inertia. And I've noted these with MT for maritime transportation projects and ST for surface transportation or highway bridges. And you'll see that first of all, there is no consensus on how to design piles for the combined effects of inertia and kinematic, and what load combination factors use. And part of that is, as you see from when you look at these different design codes from ports and wharves and nearshore structures and highway bridges, is that these load combination factors are very soil and project specific. And I have some specific findings on this to show you a little later using these centrifuge tests. So as I said, we used 5 centrifuge tests that were performed by Scott Schlechter, Nathan McCullen, and Steve Dickinson when they were at Oregon State University. The tests were performed at the centrifuge facility at UC Davis. Here is a figure of one of these tests. Right here, you see the deck supported by 3 by 7 rows of piles. Here is a cross section of one of these centrifuge tests, which were loaded with strain gauges along the piles, accelerometers at the wharf deck, which we use to see when the maximum inertia occurs, displacement transducers that measure displacement on the deck and soil, and pore water pressure transducers that tells us when liquefaction occurs, as well as accelerometers embedded in soil, which we use to back calculate the soil displacements. Just to give you an idea of the general geometry, we have dense sand on top, 2 rock fields, a dense sand on top, about 16 meters of liquefiable soil, and underneath is another dense sand. And these are 7 piles, so you're looking at the cross section, and there are 3 rows, as you can kind of see here in this photo here, 1, 2, and 3 rows of piles. The pile diameters range from 0.4 to 0.6 meter. I think I have it here. So these are layouts of the other centrifuge tests. So they all have a 3 by 7 pile group. The diameters are 0.4 to 0.6 meters. And they were designed to be a representative of concrete piles in prototype scale. So this is one of the tests that I showed you earlier. There are 3 tests that are kind of similar: NJMO1, this one NJMO2, and this one to the right, SMSO1. So they all have a rock field, 2 rock fields, loose sand in the middle. In some of these tests, an effect of ground improvement was investigated. So in this middle left figure, you see a bay mod. So this was supposed to investigate the subsurface conditions at the port of Oakland. And then in the SMSO1 middle right, there is a CDSM, a soil deep cement soil mix, or deep soil cement mixing as an improvement for bay mud. Which interestingly, this CDSM unit was not keyed in the underlying dense sand layer. And a failure surface developed right underneath this CDSM unit, which resulted in huge bending moments on these piles. And 2 tests at the bottom, one of them a rock field. This one is an interesting case because it represents a non-liquefied condition. It's a rock field and a dense sand. And to the right of that is a thin rock field sitting on a loose sand, and then a dense sand in the backland. We looked at the failure surface, and you can kind of see with these red dashed lines, and those would tell us where the bending moments develop, and we use that to look at to define the critical cycle when the maximum bending moments develop, to then look at the combination of inertia and kinematic. Here I have an animation that shows one of these centrifuge tests, and this is not a simulation. These are all recorded data from the centrifuge test. So at the bottom you see the ground motion. This is Loma Prieta scaled to 0.15 G. You see the deck displacement moving, so that's the acceleration of the deck multiplied by the mass of the deck is the source of the inertial load. You see these pink lines show how the soil displacement is moving based on back calculated from the accelerometers that were embedded here, and you can kind of visually see how the soil moves and the deck moves and how they interact, and whether if they are in phase or out of phase during the motion. On the right side, you see the pore pressure ratios, and right here is 100%. If my cursor moves, okay, so here is 100%. So right in this loose sand layer, we will see that it liquefied. Closer to the piles, it didn't really reach to 100% pore pressure ratio, which I'll show you a little later. I'm going to go to next slide, but if you want at the end of the presentation, I can play this animation one more time. So we looked at the moments that were recorded in the strain gauges, and here you see in gray all the moments that were recorded during the time history. And we classified them into the moments that developed at top of the pile. Let me see if I can get that pointer. Okay, I'm trying to get the pointer to work. Okay, so there are bending moments that are shown with that blue hatched area that develop at top of the piles. And then there are bending moments that developed deep in the soil, as deep as 26 diameter deep, which is way deeper than the typical depth of fixity. And there are places where the moment developed below the ground, below grade, but shallow. So we bin these into the pile head moments, the deep moments deeper than 10 diameter, and shallow moments shallower than 10 diameter depth. And this is basically compatible with what AC61 uses to define different performance criteria for pile head, in-ground moments, and in-ground moments that are shallower than 10 diameter, and in-ground moments that are deeper than 10 diameter. So as you look at this example here, you see that the moment at top of the pile was 483, in this case, kilonewton meter. And at depth, it was 768. So this is one example where the moments deep into the ground, which usually developed at the top and bottom of that liquefiable layer, were actually larger than the moments that developed at top of the pile. So we try to do this for all the 5 centrifuge tests and understand where the moments develop. Are they usually larger at top of the pile and smaller at in-ground, or vice versa? So you see the results on this figure here, which shows bending moment, maximum moments in each centrifuge test. These are 5 centrifuge tests, and I'm plotting all the shaking events that we have from each test. So moment above grade versus moment below grade, and this is 1-to-1 line. And you can kind of see that with some standard deviation to the data, most of the data or the moments above the grade are fairly comparable to the maximum moments that develop below the grade. And in some cases, there are even moments, deep in-ground moments are larger than the moments that develop above the grade. So Let's look at time history of one of these cases as an example. So this is NJMO to one of those centrifuge tests as an example. And you see here the moment time histories on top, and then displacement time histories for the wharf deck in black, ground surface in red, and then RU time history. So these are pore pressure. And inside each graph, there's a little diagram that shows where the data that we're plotting is located, where the sensors are located. So you can kind of see that dashed line reaches to 100% RU. That's the far field pore pressure transducer in the liquefiable layer. And then the ones within the piles, the near field, the ones that are located near field, closer to the piles, they actually don't reach to 100% RU. They're a little smaller. But we used this far field one can give us an indication of when liquefaction triggers. And at the bottom are the accelerations, the base acceleration in black and the wharf acceleration, which is basically the indicative of our inertia force in blue. So there are two dashed lines that go vertically on this figure. One of them show when the maximum moment develops above the ground at pile head. That's based on where that blue line is maximum, and you can kind of see where that sensor is located, right at top of the pile. And there is a second dashed line that shows when that green line is maximum, which is the deep bending moment, which is right there below the rock fill, right at top of the liquefiable layer. And if you project those down and look at the wharf acceleration, there are several things that we can see here. First of all, that the wharf inertia is always in phase with the soil displacement. You can see that in the second plot right here. They're not out of phase, they're in phase. Two is that the pile head moment develops early on in the motion, and in fact it develops when the pile is moving landward. So you can kind of see that it's aligned with this point, which is when the displacements are positive or towards the land. And at that time, if I go down to the wharf acceleration, we're almost at 100% maximum inertia, maximum acceleration. Or if you do the math, it ends up being about 90% of maximum inertia. So for the moment, when the moments at top of the pile are maximum, the inertia was about 90%. It's highly correlated with the inertia as expected. If you look at the deep bending moments right here, first of all, it develops after liquefaction triggers. So RU has already reached 100%. Two, it develops when the wharf is moving downslope, as you can see by the sign of the displacements here. Three, the portion of inertia that is acting at the deck when that deep bending moment is maximum is about 40% of maximum inertia. So right here, you can kind of see what I'm going to show you on the next slide, which is there seems to be a depth dependent on these combination factors, inertia and kinematic interaction factors. For the pile, for the moments that develop at top of the pile, there seems to be a higher inertia contribution. And for the moments that develop deep into the ground, there is a smaller likelihood for that combination. So we did that for all the 5 tests, for all the key bending moments in these 5 tests, and that's what I'm plotting here. So on the vertical axis is the portion of deck acceleration. This is basically our inertial factor going from 0 to 1. On the horizontal axis, you see the centrifuge test. If my pointer starts working, okay. So one thing that you notice here is that there's huge range here. The inertia, the inertial combination factor back calculated from the centrifuge test varies from somewhere between 0.2 or 0.3 all the way to 1. The second thing that you may notice is if you look at the pile head, the shallow moments and deep moments. The pile heads are the red triangles, and shallow moments are the green circles, and the deep moments are the blue squares. And you can kind of see that the data points for pile head plot higher than compared to the deep moments, which is basically what we saw in the previous plot. There seems to be a higher inertia contribution when you're looking at the bending moments that develop at pile head, and less contribution when you look at the bending moments that develop at depth. The other thing that you may notice here is that there seems to be a difference between these three tests on the left, NJMO1, NJMO2, SMSO1, and the two tests on the right. For the ones on the left side, that contribution factor, inertial load factor, ranges from somewhere between 0.2 or 0.3 up to, if you only look at the deep moments, up to maybe 0.6. When you look at these two, that combination factor ranges between 0.9 to 100%. So there is something very soil profile dependent happening here. So we looked at these two and we tried to bin these into two classes of profiles. In one of them, we have a large kinematic demand driven by a massive non-liquefiable rock fill. In another one, you have small kinematic demands induced by a thin rock face or a non-liquefied condition. And in these cases, your combination factors are higher. So based on these analysis, these are our proposed load combination factors. Here is a portion of permanent soil displacement to be applied at the end node of PY springs. And here is a portion of peak deck inertial force applied at deck. So the first combination, load combination, is the inertia only. No kinematic and 100% of inertia. We found that this load combination is enough to estimate the bending moments that develop at pile head, and I'll talk about this in a second. The load combination C at the bottom is the kinematic only case, where you apply 100% of displacements to the PY springs and no inertia on top, and we found that this is enough to estimate the bending moments that develop at depth, 10 diameter and deeper. For the shallow bending moments, we found that you need to combine inertia and kinematic. So for cases that are similar to profile B1, and I'll show you these profiles in the next page, but for these ones, that combination factor is somewhere between 30% to 60%. And for the ones that look like profile B2, that combination is between 90% to 100%. So what are these profiles? This is kind of an example of those. So B1 is when you have a deep-seated liquefaction underlying significant non-liquefiable cross. So here is where that deep-seated liquefaction occurs. You have a huge rock field that exerts a huge kinematic load on the piles. In these cases, your kinematic load is large, but the load combination factors with inertia is smaller. Profile B2 is when you have generally smaller kinematic demands or loads associated with either non-liquefiable profile or weak or softened soil closer to the ground surface. That basically this loose sand layer, and a thin rock fill. In these cases, the kinematic loads are smaller, but the contribution of inertia and kinematic is larger. So with that, we said, well, all right, how do we do the design in an equivalent static analysis using a PY approach? In order to do that analysis, we need to estimate inertial demand and the kinematic demand. But before doing that, we wanted to see how accurate is a PY approach in estimating demands, specifically in this case, bending moments in the piles. And we all know the limitations with the PY approach. The PY springs do not capture the dynamic behavior of soil structure interaction. There are issues with the way that they model loading and unloading, development of the gap. There are issues with the way that the original PY springs have been developed for small diameter piles, so can we apply them to large diameters or not? So that's also a question. But I want to show you here an example of where we wanted to see how well we can, what is our baseline for estimating the bending moments if you use a PY approach. In this case, we used L-pile. And we got the deck accelerations from centrifuge and the soil displacements from centrifuge, and we applied them in L-pile. So there's no uncertainty associated with how to estimate these two demands. And as you can see, the centrifuge bending moments are shown with those symbols, and they're captured reasonably well with the L-pile PY approach. And there are different types of L-pile analysis that I'm doing here. I'm talking about them in a little bit. There's applying inertia only, kinematic only, or a combined case. But if you look at case pile 1, for example, these deep moments and the pile head moments are reasonably captured with this. So we think that capturing maximum bending moments using PY solutions is reasonable. Can we capture the intermediate behavior during the dynamic motion with the PY approach? That's a little questionable, but at least the maximum bending demands are estimated reasonably well. So now we're going to discuss how to get these two main components, the kinematic demand and the inertia demand. So there are several design questions that I'm going to go through as I discuss this section. First of all, how do we apply kinematic demands? Displacement base versus limit soil pressure. So this is the same figure that I showed you earlier. One approach, as you know, is when you get the soil displacement and you apply them to the end node of PY springs, and then you look at the demands in the piles. The second approach is to remove all the PY springs and apply a limit or ultimate soil pressure on the piles and estimate the demands. Well, we found, as I said earlier, that this ends up being overly conservative in our case, and I'll show you why. These are the soil reactions that are back calculated from one of the centrifuge tests in 2 events actually, so the results are fairly consistent. And at the time when inertia is pushing downslope, so inertia is pushing to the left, but when you look at the soil resistance or the soil reaction, it's actually resisting in the almost top half of the rock field, and it's pushing down in the lower half of the rock field. So it's nowhere near to a uniformly downslope earth pressure or soil pressure that we would use if you're using the limit soil approach. And as you can see that if you, instead of this, if you apply a uniformly downslope soil pressure, you're going to overestimate demands by a huge amount. So this is a case when you have a small diameter flexible piles, because flexible piles tend to follow soil deformations. This conclusion that I just said here may not be the case when you're dealing with a large diameter piles, and we can get into that if needed. Here, I'm showing you why that soil reaction is the way I showed you earlier. So on the left, these are back calculated soil displacements and pile displacements from centrifuge tests. So they're not simulation or L-pile analysis. These are back calculated from the tests themselves. So red shows how the soil moves, blue shows how the pile moves, and as you see, there are locations where the pile moves more than the soil, which is why the soil reaction pushes up in a positive direction, and there are areas where the soil moves more than the pile, which is why the soil reaction is moving downslope in the negative direction. Now over here, I have this red line which shows the ultimate soil reaction. If you take the P ultimates of the PY springs from API and plot it here, you can see that the soil reactions that we back calculated from centrifuge are just way smaller than the P ultimates that you would estimate from PY curves, from API curves. This figure to the right of that is the same figure with just different scales, so you can kind of see the P ultimate from the API curves if you choose to use the ultimate soil pressure and apply them as a kinematic force. And you can see that it's just you would overestimate the demands by significant amount if you use the red curve as opposed to the displacement approach, which might give you something closer to the blue demands. So the second question is, so going back, our recommendation is to use a displacement-based approach and apply the pile restrained soil displacement to the end node of PY springs. Now, let's focus on that pile restrained issue. Some people believe that we should apply the free field displacements to the end node of PY springs. Some people believe that we should apply the pile restrained soil displacements, accounting for pile pinning effects. Caltrans 2012 recommends using the pile restrained displacements, and I wanted to show you what happens if you use either of these two displacements. I'm showing you a different project, different study. This is from when I worked at Fugro, and I'm showing you just as an example to see what happens if you use either of these two loads. So this is from an Amber Cove cruise ship docking facility in Dominican Republic. There's a 400 meter of a main pier supported on 30 bends, and then a trestle right here on 200 meter long, supported on 17 bends. And the bends look like this. So they're a pile group that look like here, 3 piles. Again, relatively flexible piles, 0.76 meter diameters. And we performed FLAC analysis, nonlinear dynamic analysis. On the top, you see the soil displacements without the piles, 3.5 meter of soil slope toe displacement. At the bottom, you see if we add the piles. So these are the pile restrained, what Caltrans calls the pile restrained displacements, about 0.4 meters. So 3.5 meter soil displacement free field compared to 0.4 meter of pile restrained displacements. And now let's see what happens if you apply them in L-pile. On the left, this is a result of a pseudostatic analysis. You take those soil displacements and apply them in L-pile. On the left, you see the soil displacements in dashed blue line. So that's a 3.5 meter that I showed you earlier. And the pile displacements that you would estimate from that are these really large displacements, whereas in the dynamic analysis, we recorded this much displacement, less than 0.5 meter displacement at the top of the pile. Now, if instead of free field displacements, we apply the pile restrained displacements, then you get something that is much closer to what you measure in the dynamic analysis. So red is the displacements, estimate the pile restrained displacements, accounting for pile pinning effect applied in L-pile. So that would just give you one point of reference, and I'm sure that a lot of you are familiar with this difference, that the free field displacements versus pile restrained displacements could be huge. The other design question, so just going back again, our recommendation, as you'll see later, is to use the pile restrained displacements. Now, if you're trying to estimate the displacements, how do we estimate them? We usually use Newmark block analysis. We wanted to see how to estimate what displacements are these Newmark block analysis really represent. So what you see here are the maximum transient versus permanent displacements. So on top are the soil displacements, at the bottom are pile bending moments, and you can these are just measurements from the centrifuge test. And you can very clearly see that the maximum bending moments are correlated with maximum transient soil displacements, and the smaller bending moments at the end of a motion are correlated with the permanent displacements that occur at the end of a motion. So if you're interested to know the maximum moment that develop in the pile during the ground motion, you would need to estimate the maximum transient soil displacements that occur in the piles. For relatively flexible piles, this is very important because the bending moments are almost linearly, maybe not linearly, but very strongly proportional to the soil displacements because they follow the soil displacement pattern. So we wanted to see, when we perform a Newmark block analysis, do we estimate this one or permanent one, and by what measure of accuracy? So here you see the results of one of our master students, Thomas Torkelson, using Newmark sliding block analysis to get the pile restrained soil displacements. Caltrans recommends using the compatibility approach, where you actually perform a pile pinning and you get the shear forces from an a lateral load analysis, in this case L-pile, and you input them in your slope W analysis or slope stability analysis. That's what we did here. If you're curious, we used the residual shear strengths in liquefiable soils, which was compatible with the weighted approach that Steve Kramer recommends in his 2008 WashDOT report, and they worked out pretty well in estimating displacements. So in this figure at the bottom, you see the soil displacements with time. Blue is the recorded displacement from centrifuge, and the green are the ones that we estimate using Newmark block analysis. And you see that there's quite a bit of variation here. So we looked at the mean or median displacements from Newmark and median plus one standard deviation, and tried to see which one estimates the maximum transient or permanent soil displacements better. So what you see here is the results from all the 5 centrifuge tests and 2 shaking per test, so 10 experiments total. These are all Newmark displacements versus centrifuge displacements. On the left is the permanent end of shaking displacements. On the right are the maximum transient displacements. As you can see, if you're interested in the permanent end of shaking displacements, the median displacements from Newmark analysis on average captures the permanent displacements from centrifuge reasonably well. If you're interested in maximum transient, then we have to use median plus 1 standard deviation, which are shown by these tick marks on these, the ranges that you see in these plots. So maximum transient, just to put in writing, maximum transient is better estimated using median plus 1 standard deviation from Newmark analysis. Permanent displacements are reasonably captured using median values from Newmark. But there's a caveat here. So if you're interested in maximum moments, we should be using maximum transient displacements. If you're interested in maximum transient displacements, our data shows that we should be using Newmark method, median plus 1 standard deviations. But when you get the soil displacement at the ground surface, you have to distribute them with depth. And there's quite a bit of uncertainty in how you distribute them with depth. So here you see the displacements estimated from the centrifuge test in red, and displacements distributed with depth in our design approach using the median displacements that are underestimating the centrifuge displacements. But if you notice here, there is a sharp transition at the layer boundary when you're using an idealized design profile. These sharp transitions, which do not really exist in the experimental data, result in overestimating the bending moments. So we found that the underestimating the maximum transient displacements is almost canceled out by overestimating the mass due to these sharp transitions. And at the end, our design recommendation was to just use the median Newmark values and combine that with idealized displacement profiles, and that should give us a reasonable estimate of bending moments. And by the way, we are to distribute the ground surface displacements that you get from the Newmark with depth, we followed the method that was published by Armstrong, Boulanger, and Beatty in their 2014 paper. And it pretty much ended up being constant within the non-liquefiable rock field, and then linearly decreasing within the liquefiable soil, and then constant within the dense soil, which you would probably use the same approach in design anyway. But this is specifically in this case, that was our finding. There are other cases where their approach might give a better estimate of the displacement profile. So now that we have a way to estimate the kinematic demands, we want to see how to estimate the inertial demands. So we use pseudostatic analysis or pushover analysis. We know that liquefaction affects spectral acceleration, but these effects depend on the timing of liquefaction triggering. Plus, there are questions whether when you're doing a pushover analysis, do you use a softened soil properties, accounting for the effect of liquefaction, or using the non-liquefied conditions. Caltrans recommends estimating inertial demands from a non-liquefied conditions using pushover analysis that is done with the non-liquefied soil properties, and then modifying it with the effect of liquefaction. We tried both. So we performed our pushover analysis using non-liquefied conditions, and we also performed the analysis with the liquefied conditions, where we applied soil displacements to the end node of PY Springs. And those soil displacements, again, following our previous recommendation, we were using the mean Newmark values, and we are using idealized soil profile displacements with sharp edges. And we're also applying P multipliers in the liquefied soil. So these are our pushover curves in the non-liquefied condition and liquefied condition for all the 5 tests. You can see that the stiffness of the curves are softened due to the effect of liquefaction and the soil displacements that are applied due to kinematic demands. And then we use the pseudostatic analysis to estimate the wharf acceleration. So these 2 figures show the spectral accelerations from the equivalent static analysis from pushover analysis on the vertical axis, and the recorded peak wharf acceleration on the horizontal axis recorded from centrifuge tests. On the left, you see the non-liquefied pushover analysis. On the right, you see the liquefied, using liquefied pushover analysis. And overall, we found that there is no significant difference between doing the pushover and performing a pseudostatic analysis with liquefied versus non-liquefied conditions for these tests that we analyzed here. On average, they ended up being estimating the wharf displacements, accelerations pretty well. One thing to notice is that we found that we have to use a higher damping ratio for the spectral accelerations to be able to estimate a reasonable maximum wharf acceleration. So something close to 15% as opposed to a typical 5% that is used in design. And we have justifications for this using this equivalent static analysis that I'm showing here, and later we did a FLAC analysis, nonlinear dynamic analysis in FLAC, and again we came up with the same conclusions. And this added damping could be attributed to radiation damping and the soil pile fluid interaction that we don't normally capture with a 5% damping ratio, but it's something to be considered with the structural and geotechnical engineers on the project. One thing to note is that if you end up using a non-liquefied pushover analysis to estimate inertial demands, you need to make sure that you account for the effect of liquefaction on the wharf spectral acceleration. Caltrans, as outlined in this peer report, or the Ashford et al. 2011, recommends that you get the I non-liq, which is the inertia in the non-liquefied case, and modify it with this C-liq, which accounts for the effect of liquefaction. And you see that C-liq ranges from 1.4 to 0.35 for pile cap, or 0.75 to 0.45 for superstructure, for different type of ground motions with different spectral shapes. So now that we have an estimate of our inertial demand and a kinematic demand, we wanted to see how to combine them and where we actually need to combine them. So we performed our pseudostatic analysis in L-pile in 3 different ways. Case A is when we only apply the inertia at top, 100% of inertial load. Case C is when we only applied kinematic demands and no inertia. So kinematic demands being the mean Newmark displacements applied to the end node of PY Springs, combined with the idealized soil displacement profiles, and softened PY Springs within the liquefiable soil using P multiplier approach. And third case, case B, which is a combined 100% of kinematic with some portion of inertia at top of the piles at the deck. And this is what we see. So these are all bending moment comparisons. Bending moments estimated from L-pile on the vertical axis, bending moments measured in centrifuge on the horizontal axis. The left figure is when we only look at the bending moments that develop at pile head. The right figure are the deep bending moments that develop at depth. And these are the 3 cases. So if you only look at the left figure for the moments that develop at pile head, you'll notice that if you apply kinematic only, 100% of kinematic only, we would be, as expected, we would underestimate demands because the bending moments at pile head are heavily influenced by the inertial load. So if you don't apply the inertial load, we would underestimate them. On the other hand, if you see when we apply the 100% of inertia only, shown with the green plus symbols, we actually end up estimating the measured displacements reasonably well. And on average, we're actually, on average, we estimate them reasonably well. If you look at the bending moments that develop at depth deeper than 10 diameters, then applying inertia only obviously is not going to develop to estimate the bending moments that develop at depth. But if you only apply kinematic only with no inertia, you actually get a pretty good estimate of the bending moments. And adding inertia, in this case 85%, just as an example of inertia, doesn't really increase the accuracy of those estimates. So we use this as a basis to suggest that if you're interested in pile head moments, applying inertia only is enough. If you're interested in deep moments that develop deeper than 10 diameters, it seems like applying the kinematic only or displacement only case is enough. So with the next thing that I want to discuss is that now that we have some estimate on the inertia and kinematic interaction using centrifuge tests that were performed primarily using short duration motions, we wanted to see the effect of long duration motions on this interaction. We all guess based on the AASHTO and the other codes, we know that this combination is likely to be higher, but we wanted to see if that is really the case with the analysis. So what we did, we used nonlinear dynamic analysis in FLAC. We took one of those centrifuge tests, we made a FLAC model, we calibrated it based on the centrifuge test data, and then we subjected that calibrated model to a suite of short and long duration motions that are spectrally matched to have the exact same spectra, but different strong motion durations. We used constitutive model that we use for liquefiable sand is the PDMY03. This is the model that I work with Professor El Gamal and his team, and we published it in 2018. Professor El Gamal and his team, they've implemented this model in FLAC, FLAC 3D, ANSYS, and a bunch of other different platforms. And you can check them out in their website, soilquake.net. One thing that we added to this model in PDMY03 compared to the previous versions was that we modified the model that when you look at the CSR versus number of uniform cycles to reach the liquefaction, we were able to reduce the slope of the line or the B value to be more representative of the experimental data, somewhere close to 0.33, which is what you would expect to get for sand soils. Potentially for long duration motions, that could make a difference to model with a lower B value. So we calibrated against one of the centrifuge tests. We wanted to make sure that we get the soil displacements right and the deck accelerations right. So here you see a comparison of the soil displacements. Top is the centrifuge, bottom is from FLAC. We get some aspects of the behavior right, some of them not so good, but in terms of the key mechanisms which are important for us, the soil displacements and the deck accelerations, we're capturing it reasonably well. Then we subjected them to a whole bunch of gram motions that are spectrally matched. So these are shown on the left side. Those are the spectra of the seed motions, and we spectrally match them so that they all have the same spectra. In this case, I'm showing you the target spectra developed based on AASHTO, which is 975-year return period, developed for a hypothetical site in Portland, Oregon. And you can kind of see the duration of these motions. It ranges from shallow cross-hole motions with a duration of 4 seconds, all the way to like Tohoku type motions with the duration or strong motion duration D595 of up to 85 seconds. The benefit of using these motions is that now that they all have the same spectra, they induce the same or comparable amount of inertial effect, and the only difference would be the duration. So we can kind of use that to see how that interaction changes. So I only have a few more slides to say here, but here is this is a commentary on the from the Canadian Highway Bridge Design Code S6 2019. And I'm quoting here: in large magnitude earthquakes, higher likelihood that strong ground motions will continue following liquefaction triggering. And we totally see that using these results. Here you see the deck acceleration and RU, which tells us when the liquefaction triggers. The top red is the short duration motion, and the bottom one are the long duration motion. So here is where liquefaction triggers, indicated by 100% RU. And you can kind of see that after that, in a short duration motion, we barely get any inertial cycle. Whereas if you look at the long duration motion, liquefaction triggers here around 24 seconds. And after that, we still get a lot of strong inertial cycles. And in fact, the maximum inertia occurs, somewhere around here, closer to 70 seconds, way after triggering liquefaction. So we use that to do what I showed you earlier with the centrifuge recordings, back calculating this inertial combination factor. So if you think about 100% of kinematic with some percentage of inertia, that some percentage is plotted on the vertical axis here, and on the horizontal axis is the duration. I'm plotting the data from our centrifuge test just as a reference. So you can see those 2 tests that had really high combination factors and 3 tests that had a lower combination factors. And I'm also plotting data from our FLAC analysis, which you can kind of see that this combination factor increases as ground motion duration increases. Now, ideally, we would want to have more data points here with the long duration points, but I want to show you another case where we perform. Now, this slide that I showed you here, this is from the pile-supported wharfs. Now, this is another study where my former student, Jonathan Nasser, did, and he used nonlinear dynamic analysis in a different platform in OpenSeas on a totally different pile foundation. This is a 2-meter diameter pile shaft, typically used for highway bridge foundations. Very different soil subsurface conditions: stiff cross sitting on liquefiable soil, sitting on dense sand at the bottom. And if you look at the load combination factors, inertial combination factor on the vertical axis versus duration, we also see the same pattern, increasing pattern with duration, which is just another way to say that when you're dealing with long duration subduction earthquakes, there is a higher likelihood for inertia and kinematic to interact. We calculated that for short duration earthquakes, with or without pulse, we get about 60% inertia contribution, and that increased to about 75%. So roughly 15% increase when we're dealing with long duration earthquakes. And if I go back to the previous slide, the same thing we notice here too. We go something from about 60% in the short duration ones to something close to 75% in long duration ones. Something to add here is the difference between something specific to flexible piles. In relatively flexible piles, when we have small diameters, closely grouped piles, such as what we typically see for wharves and ports, kinematic demands dominate the response in long duration subduction motion. So here you see FLAC analysis for 3 different cases. Case A is our typical case when we have liquefaction and deck mass, and we get the combination of the 2 effects. Case B is when we only have the deck inertia. So we turned off liquefaction, we make the soil to behave as drained. So we get very little kinematic effect, no liquefaction, and we only get inertia. And case C is kinematic only when we set the deck mass to be 0, but we get liquefaction, and liquefaction induced lateral ground deformations. When you compare the short duration on top versus the long duration motion at the bottom, you see that in a short duration motion, we get quite a bit of contribution from inertial force. Whereas when you look at the long duration, the red, which is the kinematic only, pretty much dominates the pile or the wharf response. So even though you get small cycles of inertia, but pretty much most of the wharf displacements are governed by that kinematic effect. So this is just to say that even though in long duration subduction motions, even though we get larger inertia contributions, the inertia interaction factors, the contribution of inertia reduces and becomes less important, and kinematic really becomes the driving force and dominates the response. So just to wrap it up, some conclusions and some recommendations to be considered in your projects in design. Bending moments adjacent to pile head can be reasonably estimated by applying peak inertial load only, while bending moments at deep locations, deeper than 10 diameter, can be reasonably estimated by applying the kinematic demands only. Bending moments at shallow depth, shallower than 10 diameter, can be reasonably estimated by combining kinematic demands with a portion of peak deck inertial load, which ranges from 0.3 to 0.6 for profiles that resemble profile B1, and much higher, 0.9 to 9, which for profiles that look more like profile B2. And just as a reminder, these are the two profiles. Profile B1 is when you have a deep-seated liquefaction underlying a thick non-liquefiable crust. Profile B2 is when you have a shallow liquefaction with a relatively small or thin rock fill or a riprap, or just non-liquefied conditions. The wide range of this inertial multiplier that is observed in this research highlights the benefit of performing coupled nonlinear dynamic analysis. So if this combination factor is really driving your foundation concepts and demands, it might be worth it to perform a nonlinear dynamic analysis to really capture this complex soil structure pile interaction for the exact site-specific soil profile that you have at your site. These load combination factors that are proposed here are only appropriate for decoupled analysis when you're using a PY spring approach, are not necessarily appropriate for the cases where you're using a simplified equivalent fluid pressure, or if you're using a limit pressure approach, because as I said, there's a built-in conservatism using the fluid pressure or limit pressure approach. It is recommended that the median displacements computed using Newmark type analysis be applied in combination with the idealized soil profiles with distinct transitions. The analysis in this study suggests the likelihood of inertial load interacting with kinematic loads increase with motion duration. So we noticed about 15% increase going from short duration to long duration motions. However, it was found that the behavior of wharf structures supported on relatively flexible small diameter piles, which follow the ground deformations very closely, is heavily influenced by the kinematic loads in long duration motions and less so by the inertial loads. And the last thing on that damping ratio, the modeling that was performed in this investigation supports the use of damping ratio significantly greater than the 5% that is routinely used in practice as a basis for spectral accelerations. Given the range of tolerable and anticipated displacements that are defined in ports, codes, and standards, for design level ground motions, a damping ratio of approximately something higher, say something between 10 to 15%, appears to be more suitably representative of the aspects of wharf and pile foundation and soil behavior. And at the end, I'd like to acknowledge our collaborators, Steve Dickinson from New Albion Geotechnical and formerly at Oregon State University, Nathan McCullough, Jacobs, and Scott Schlechter at GRI, that they really provided this amazing set of data from centrifuge tests and collaborated with us over the past 4 years to in this study. And the funding was provided by the Deep Foundation Institute, and as part of the Seismic and Lateral Load Committee, the National Science Foundation, both the centrifuge tests that were performed by Steve back then, and the recent analysis that was done by me and my students were supported by the National Science Foundation.